Bastien. Nick Cohen's at McGill and Bastien here at University of Montreal. His research focused on the characterization of exoplanet atmosphere, in particular the very hottest of the hot Jupiters. And actually, he will talk today about WASP-12, which is the perfect example of this. It's a planet that is something like 2,800 Kelvin or so. He does most of his research with the Hubble Space Telescope, with the Spitzer Space Telescope, and I think today we're going to talk about a Spitzer result, right?
Yeah.
Okay, great. Yeah, I mean, that's basically, and you're in your third year right now? Third year?
Yeah,
okay.
yeah, third year.
Okay, then I open the floor to you, and yeah, I'm looking forward to the presentation.
Okay. So I'm talking about WASP-12b, which has an acronym, but I prefer to use this new acronym that I have recently realized that it could stand for, and that is What a Strange Planet. So this is a really unusual planet, and I'll hope to convince you of that throughout this. But first, let's just go through a quick introduction. So WASP-12b is a Jupiter-sized planet. It has a mass of 1.5 times that of Jupiter, which is pretty similar, but it has a radius of nearly twice that of Jupiter. And so for those of you who don't work with Jupiter-sized planets much, as you approach the mass of Jupiter, you don't expect the radius to grow significantly. And then as you grow beyond the mass of Jupiter, until you start having M-dwarfs and things like that, you expect the radius to actually decrease as you increase mass. So the fact that this is much larger than Jupiter, but slightly more massive, means that it's really puffy. It's very inflated, and it's much more inflated than we would expect it to be, which is a common phenomenon with a lot of hot Jupiters. And it is indeed a hot Jupiter-sized planet. Its day-side temperature is an aggressive 2,800 Kelvin, and its night side is slightly less aggressively hot at 1,600 Kelvin. This makes it, I think, the third or fourth hottest planet the third or fourth hottest gas giant that we know to date. And that's because it orbits one stellar diameter above the surface of its star. It's remarkably close to its star. And its star is about a G0 dwarf, so it's a very sun-like star. And it's the prototype for a class that we've recently realized of exoplanets of ultra-hot Jupiters, not just hot, but ultra-hot. And these are planets that are so hot that their day sides, these planets are primarily made of molecular hydrogen, but when the molecules get to 2,800 Kelvin, they thermally dissociate and become atomic hydrogen. And so on the day side of the planet, you have something that's more like a star, and on the night side, you have something that's more like a traditional planet. And this can cause all kinds of unusual things. I previously had a paper on how the fact that the wind's dragging this atomic hydrogen around to the night side will cause it to recombine, which releases a lot of heat. And then when it's dissociated coming back around, that absorbs a lot of heat, and that can help transport heat. So one of the unusual aspects of WASP-12b is that its orbit appears to be shrinking. So here we have many transits of WASP-12b from many different papers, all combined in this Patchwork 2017 paper. And they've tried to fit the orbit with a constant period. And if you look at the residuals of the timing of the transits with respect to that constant period, you see this downward curvature. And this is indicative of the timing between the transits becoming shorter. But if you look at the timing of the eclipses, they are equally consistent with the planet inspiraling, with its orbit decaying, or with the orbit being on a slightly elongated ellipsoidal orbit and that elongation processing. So it's not clear what is happening here. The star is expected to be about, I don't know, billions of years old. So for it to be decaying now and be so close to in spiral seems overly fortuitous, but it's a big universe maybe. Also, in order for it to decay that rapidly, as we would see it here, there needs to be more happenings. There needs to be a lot more drag in the star than we expect there to be. The star needs to dissipate the planet's angular momentum more efficiently than we expect. So some have suggested that the star is has different layers on the inside. It's not, it's not the star that we expect it to be. Given Gaia data, it's not the stellar type we expect it to be, but that doesn't make a lot of sense. And for it to be precessing, it has to be on a very small eccentricity orbit, which would have a almost immediate circularization timescale. So for it to be billions of years old and still be on this slightly elliptical orbit, we would need some kind of mechanism of sustaining an elliptical orbit so close to its star. So something weird is happening with this system.
Can I ask
Yeah.
a question now about this slide?
Yep.
Yeah. At any individual epoch on either the top or the bottom plot, how should I interpret the variation of the data points? Is this all from a single instrument? Is it systematic? Is it random? Is it from stellar variability?
I believe it would primarily be systematic. I mean, if you just shot noise. If my understanding is that those error bars are just shot noise.
Yeah, but the variation of the data points.
Yeah.
That's sort of 1 sigma, I guess. But
yeah, so if you look at the swath of them, it looks roughly like everything's normally distributed about the curves. Nothing about this immediately screams to me that there's extra stuff in there beyond this kind of downward curvature. But yeah, so these are all from ground and space-based observations. You have Spitzer, Hubble, and many ground-based observatories contributing to this. And WASP-12 is a 12th magnitude star, I believe, so it's very faint. And so trying to get enough photometric precision that you can accurately measure both the eclipse and or transit is very challenging.
Right.
Yeah. So just getting enough precision to know when it has started to dip is difficult. And yeah, please, if anyone has questions, I'm happy to take them throughout. Moving on, the planet appears to be losing mass more rapidly than any other planet that we know of to date. Can you see my mouse when I move it on the screen?
Yep, we can see it.
Yes.
Awesome. So this black line here is the timing and the depth of the optical transit of WASP-12b. And then in black and red are 2 different visits of ultraviolet observations of the system. So let's just focus on the black to start with arbitrarily. I think it was the first one anyways. So you see that it starts potentially dipping before transit, and then at mid-transit, it's at least twice as deep as the planet's physical radius is seen at optical wavelengths. And then it dips back up. And when they looked at it in a second visit, there's this huge depth of some huge absorption before transit, and then it ticks up and then ticks down. So it's not really clear what's happening, but the general consensus is that there is a gas that is surrounding the planet and is beyond just the visible radius of the planet. The diffuse gas is more absorptive at near ultraviolet wavelengths. And so that's partly why it's deeper during transit. But then there's also either this trail of gas that's flowing ahead of the planet, or some people believe that there's a bow shock happening ahead of the planet's orbit, kind of in line with it. It's more over here, which, yeah, this streaming gas, or this bow shock that has been gas stripped from the planet and is over here and is being shocked by the certain stellar medium, the stellar winds and things like that. That is causing these ultraviolet dips. So we know that the planet seems to be either elliptically orbiting or inspiraling, and we see that it's losing mass. And these losing mass and orbital decay are actually on similar timescales, which may or may not be interesting. And now we'll move on to where my work lay with this, one of my works with this planet lay. So here I've plotted a typical Spitzer phase curve. It's HD 189 733b from Knudsen 2012. And so you, at the top panel, you see the raw data. You see an eclipse here when the planet passes behind the star. You see kind of another eclipse here when it passes behind again. And then you see nice and cleanly this deep transit. But one of the things that catches your eye is this sawtoothing back and forth here and these big jump discontinuities. And this is because there's a lot of non-uniform sensitivity in the Spitzer pixels. So this isn't due to the star being on multiple pixels and different pixels responding separately. This is the center of the pixel being more sensitive than the edge of the pixel. And so as the spacecraft is up in space, jiggling back and forth, it has this sawtoothing motion. So thankfully, this is fairly easy to model and understand. And so we can fit this with different systematics models. And some people scream, that's bloody murder, dangerous, whatever. But the hope is that if you try enough things, you marginalize over them, and you fit these systematics simultaneously with your astrophysical model, you'll do the best we can do. And then after modeling all of those systematics, you get this nice, smooth sinusoidal phase curve where you see a peak when you see the hottest hemisphere of the planet, a minimum when you see the coldest hemisphere. And if you look really closely, the peak isn't exactly at eclipse, it's slightly before, and that's indicative of winds blowing the hot gas to the east, and before it cools down, it's dragged over there. So you see this peak before. In 2010, so now we move on to a WASP-12 phase curve, and just for simplicity, I haven't shown my raw data, but it looks very similar to this, lots of sawtoothing. In 2010, a phase curve of WASP-12b was taken in 3.6 and 4.5 microns. For now, I'm just showing 3.6. And if you look at it, that looks very similar to the phase curve I just showed you. There's a peak slightly before eclipse, there's a deep transit, there's eclipses, and there's just a nice sinusoidal phase curve. Except this planet is 2,800 Kelvin degrees on the day side. And so our expectation is that the radiative timescale of the gas is so fast that we wouldn't anticipate any appreciable offset. We would expect most of the hottest hemisphere to be aligned with the illuminated hemisphere. Perhaps hydrogen dissociation is playing a role in that. Maybe that's why it's pulled over, and it's pulled over by a lot. But that's something. Now, if we show you the 4.5 microns, you see that there's this peak after eclipse. So if you just look at that, it looks like the winds are kind of maybe blowing the wrong way. Except if you look at this eclipse over here, it peaks both before and after an eclipse. There's 2 peaks per orbital period. So it's a sine 2 theta kind of a phase curve rather than a sine theta. Different things could potentially explain that. It could be a tidally distorted planet. It could be one of many things, but there's always that Spitzer systematics. And so when Nick Cowan published this back in 2012, the general suspicion was that maybe the planet is tidally distorted. We expect it to be about 7 or 8% elongated towards the star. So perhaps part of this is due to tidal distortion, and we don't see it here, perhaps because of just noise or systematics. Perhaps it's worse than that, and this is actually the amplitude of the second order sinusoidal variations, which you'd expect. This is 4.5 microns, which is the more reliable channel, but it wasn't clear. So the phase curves of this planet were taken again in 2013, and they look remarkably similar. You have a single peaked sinusoid peaking, this time to the west, the wrong direction, and this is a 6 sigma change from east to west. Perhaps that's indicative of something happening on the planet. Perhaps it's weather, perhaps it's clouds, perhaps it's systematics. But this 4.5 micron double peak did not go away. It's still there, and this has never been seen at this amplitude. So we can't point our finger at Spitzer. This is something else. So perhaps it's the planet being tidally distorted. So if we plot the radius of the planet seen at transit, this is the radius that we would see. If you're looking in this direction, this is a transit radius. And in this direction over here is the sun, the star. If we plot the amount of expected tidal distortion, you get out to this ever so slightly increased radius. So you expect some amount of tidal distortion. This is among the most tidally distorted planets that we know of. But then if you try to fit this 2 peaks with just a tidally distorted shape, you end up with this huge like rugby ball shaped thing. And I like now putting this Jupiter image over top of it to just really visually explain how ridiculous that shape is. That is so unbelievably distorted, and that doesn't look like a planet to me. Let alone this is the L1 point here, this is the Roche lobe of the planet, and it would have to stick out beyond the Roche lobe, and so it would be losing mass in that way. And yeah, it's just not at all what you would expect. So we can pretty confidently rule out just a simple geometric shape effect. And then we're left scratching ahead, what could it possibly be? The only thing that I have found that can stick is radiation from gas stripped from the planet. So as I mentioned before, we know the planet is losing mass. It's losing mass more rapidly than most other planets, maybe all other planets that we know of. But people generally expect the gas to flow ahead and spiral in on kind of a ballistic trajectory. But given the timing of these peaks, which happen exactly at quadrature within 4 degrees, we know that the gas that we're probing, at least, cannot be flowing ahead on the spiraling trajectory, but has to be flowing directly either towards or away from the star. We can't distinguish, but given other observations, I suspect it would be in towards the star. And that has been modeled before in some mass loss simulations. This is for a very different type of system, but it's one system in which there is this really relatively dense stream pointed directly towards the star, and then this more diffuse tail. And if you remember those near ultraviolet observations, we don't have a lot of evidence for what happens after the transit, but perhaps there is diffuse gas kind of throughout the system, and perhaps a trail. But then the question is, why do we only see this at 4.5 microns, not 3.6? Why do you only see it at this one wavelength? And black bodies are a confusing thing, even to those who deal with them often. So here I've plotted a 3000 Kelvin body, the flux versus wavelength. This blue line here is 3.6 microns, red is 4.5. And if you look, you see 3.6 microns has more flux. And so if I do anything to the planet that's roughly in this temperature regime, if I make it hotter or if I make it colder, 3.6 microns is preferentially affected. So if I have a hotspot on the limb of the planet or something like that, then I will create peaks that are stronger at 3.6 micron than 4.5 micron. And so you would expect the double peaks to be clearly visible at 3.6 microns. Maybe you just can't see it at 4.5, but it's the exact opposite for us. So if you want black bodies to do your explaining, you have to go to extremely cold temperatures. If you have something that's about 300 Kelvin or 600 Kelvin, you have their black body radiation being close to equal. And so if we have this gas that is flowing away, if we had something that is colder than 600 Kelvin, then given our noise limits on 3.6 microns, we could have missed it and detected it at 4.5 microns. So if it was 300 Kelvin, you'll see there's a lot more flux at 4.5 microns. So perhaps that's the issue. It's just black body radiating gas, and it's really dense and flowing towards a star. But a perhaps more convenient option, given 300 Kelvin is very cold compared to the planet's 3000 Kelvin day side, is carbon monoxide. Carbon monoxide, I've plotted here its line intensity spectrum, has its strongest band at 4.5 microns, which is exactly where this one Spitzer band is, and has no features at 3.6 microns. So if you have gas streaming from the planet towards the star or equivalently away that has carbon monoxide, and it gets excited and emits, you could expect carbon monoxide emission of this stream flowing towards away from the star. And then as it orbits, you see a long, bright stream towards a small stream and a big, bright stream. And there's some difficulties with that. Carbon monoxide you expect to be dissociated in the upper layers of the planet's atmosphere as it flows off of the planet. So you would need to dissociate it on the way out and somehow recombine it. But I don't have the tools myself to describe how much flux you would expect from carbon monoxide. And so people with these mass loss models, with radiative models as well, would be better suited to say, you need the gas to be sufficient size, and perhaps we're seeing something very close to the planet. So if we go back here, perhaps we're seeing something bright and carbon monoxide emitting here, and then it turns upstream and creates that near ultraviolet absorption. And with that, I'll stop it there, and I welcome any questions.
Yeah. This is Ray. I was just wondering about how plausible it is that carbon monoxide would be escaping, because hydrogen can certainly escape given normal EUV illumination, but carbon monoxide would normally just escape if it were being dragged along with a whole lot more hydrogen escape. And so, is there any thought about the mechanisms of the CO escape?
Yeah, so for several of these planets with mass loss detected, we have high resolution spectroscopy of them during transits, which indicate that there's tentative evidence of both carbon and oxygen and other heavy metals being entrained in that gas strip from the planet. And WASP-12 is, like I said, we believe losing mass more rapidly than any other planet. So yeah, we know that carbon and oxygen and iron and these types of things do escape the atmosphere. It's not just hydrogen. And we've seen helium escaping as well. So it's definitely not unreasonable to expect there to be heavier metals escaping.
Okay, no.
All right, are there any more questions?
Well, actually, your picture of the carbon monoxide dissociation, are you saying that at those temperatures, the CO should already be dissociated before it ever has a chance to escape, or are you?
So it shouldn't be.
Carbon and oxygen is escaping. Or?
It shouldn't be thermally dissociated. Carbon monoxide is stable to about 4,000 or 5,000 Kelvin. It's the strongest molecule in existence, but the expectation or the belief is that much or most of the mass loss from WAS12b is driven by FUV flux, and the peak of that flux is, much of that flux is exactly at the dissociation energy of carbon monoxide. And so the flux that's driving the escape is expected to break apart the molecule.
Okay, yep.
So Taylor, I have also one question. You showed this 3D, or I'm not sure whether it was 3D, but it's a simulation exactly. So you said basically it would be, if it was something like this, it needed to be this small tail that is between the star and the planet.
Mm-hmm.
The long tail that is kind of in orbital direction there, though.
Yeah.
Have you like looked at what the optical depths of those are? Because I mean, it seems like that. Yeah, maybe the density is slightly higher just inside of the planet, but what is it? I guess what is this in terms of optical depth from the viewer's direction, from the direction of us? So that long tail, if you're looking into this, should also be quite.
So again, this was done per a not so similar system. It was a very short orbital period, but very short. It's WAS12 is even slightly closer than this to its host star, and it was for a relatively low mass body. I think it was more sub-Saturn size, so much lower escape velocity, and so a lot of the details of this should not be taken under assumption for WAS12b. Most of this is not well suited for WAS12b, but it's a representative model of some stream that could happen. So if you have higher flux here, perhaps you get less of this trail and it's more blown straight out. Or depending on all the balance of the system, it could be very different. Some people believe that there'll be this torus completely enveloping the star, which there is some evidence for. But yeah, and this is also a log scale too. So this more dense tail here it is significantly more dense than this. But again, I myself don't have the details of this simulation, and people would need to do a more detailed, more suited simulation to WAS12 to understand the exact trade-offs there.
I have a question, but it's more out of curiosity, I would say. When you talk about the fact that it is one of the biggest mass loss among exoplanets, what are we talking about here? Is it like as a function of the mass of the planet? What percentage of its mass does it lose per like million year or? Yeah,
so it's in that respect, I'm talking about just like kilograms per second mass loss, not
okay.
Like like time scale to demolition. But I don't remember off the top of my head. Its expected lifetime, if it is losing mass at the expected rate, is. Oh man, I can't remember off the top of my head. It's relatively short. I think it's
okay. Just if you had it off the top of your head.
I think it's more on the time scale of millions rather than billions of years.
Okay.
So it would seem fortuitous that it's losing mass this rapidly, unless there's something that's causing it to lose mass right now.
Okay, I see. Thank you.
Mm-hmm.
Since we talked last, have you had the chance to look more into the kind of the Spitzer side and seeing whether this could be explained by the kind of the AOR interruptions that Spitzer is doing during these long observations? Yeah,
so with the original observations, there was a single break in the data. A single repointing. There were two AORs. So I can't remember which side of the transit was. It was either about here before transit or about here after. As you can see, the cleaning was done quite well, and it was the same for 3.6 and 4.5. In 2013, there were two repointings happening near quadrature, which is perhaps not ideal, but the AOR style was completely different between the two. And back in 2010, there was no peak up that was done before the observations, and in 2013 there was peak up. And basically, as much as could be fiddled with was, and we've observed tens of phase curves, and to date none have shown it. And this is one of the very, very few phase curves to ever be reshot and appear the same, or at least more or less the same, with ignoring this phase offset change. So I would believe it was a miracle if somehow WASP-12 alone has this double peak, just due to some weird, unfortunate AOR timing. Yeah.
All right. So if there are no more questions, then let's thank Taylor again for this great presentation about WASP-12. It seems to be a very exciting result. So let's see also what the modelers can do with this. That would be interesting to see, as you mentioned yourself. Okay, so then let's move on to the second part of today's session. So our second speaker is Dr. Loshi Scott. He's a professional scientist or engineer at the Defense R&D Canada, Ottawa. He specialized in space situation awareness, astrodynamics, defense space systems, and space debris tracking. He regularly performs experiments with SSA using small telescope in space, also ground-based observations. And in particular, he is the mission scientist, if I understand this correctly, for HERS, so that's the High Earth Orbit Space Surveillance Satellite, and also for NEOSat, which we're actually starting also to use for exoplanets. So I think all of this is very appropriate for our TEPS meeting here today. Also, kind of making the connection between kind of the academic research at universities and the research centers, or the national research centers in the in Canada. So today he's going to talk about specifically about the defense space situational awareness R&D that he and his colleagues are working on at the Defense R&D Canada.
Great. Well, thank you very much. Just to check my audio, can you hear me okay there, Born?
Yes, it's great.
Great. All right, thank you very much. Well, to give myself a quick introduction here, I'm Lochie Scott. I work as a defense scientist for the Canadian Department of National Defense at DRDC. I am the space situational awareness lead for our defense scientific organization, and I emphasize a lot of my work on understanding what the situation is in space. Now, I'm not an astronomer. I'm a mechanical engineer in background. I got my doctorate in aerospace engineering, so I focus a lot on spacecraft themselves and what the human things that are happening in space are, and recognizing it is a changing environment right now. The traditional view of a continuously peaceful environment is oftentimes contested nowadays, and we have to spend quite a bit of time understanding and attributing what's happening in space. And some of the techniques that have been developed in astronomy have been repurposed and adopted, in some cases modified, for use on tracking objects in space. And I'll talk very briefly about that. Now, again, I'm not an exoplanet astronomer. If you're wanting to see a lot of work on the exoplanet stuff that NEOSat does, I recommend you contact Dr. Jason Rowe at University of Bishops. We task NEOSat to support that kind of work, but it's not the line of work that we inherently do within national defense. We're much more interested in what the other guy is doing, not so much what's happening naturally in space. So anyways, I'll proceed into the briefing here and just talk a little bit about space situational awareness overall. Space situational awareness, or abbreviated SSA, is based off of the old NORAD practice of building an orbital catalog. In the original days, Russia and the United States used to have to track space objects because a re-entering space object into Earth's atmosphere looks a heck of a lot like a re-entering missile. So in order to prevent an unintentional nuclear response, both of those countries maintain space surveillance sensors to watch Earth orbiting satellites, and in order to make sure that if a reentry event occurred, it didn't invoke an unnecessary and unintended response by either nation. Now, the formal definition for SSA is to basically do the foundational current predictive knowledge of characterization of space objects. That's basically saying we track objects, routinely estimate their orbits, and more recently, we predict with much more increasing frequency how often or whether or not if they're going to collide. And we produce messages called conjunction data messages in order to assess that. Now, national defense in Canada does not include asteroid objects as a part of the scope of the work. We are primarily focused on human-related activity in space, and that is the huge portion of the work that we spend most of our time on. For the work that we do in the R&D sector, we focus primarily on the security environment, protecting and defending Canadian space assets. Attributing what happened in space is a very key technical goal. To assign who actually did what in space is actually a very intractable problem. It's very difficult for us to achieve it. Responsiveness, you think since we have access to a lot of wireless technologies and so forth, talking to satellites is easy. Well, that's not really the case. We're still hampered by Kepler's law in a lot of cases that prevents us from actually doing the work as effectively in real time as we would like to do. So so some of the things that we primarily focus on is space object tracking, pattern of life, radio frequency interference, space systems capabilities, space weather when it applies to satellites, of course, and sensors and data processing are usually the areas that I focus on and my team focuses on when we work on space situational awareness. Now, there's a video that should be playing right now. I hope it's coming through okay. The situation changed in 2007 when the Chinese destroyed Fengyun 1C. What wasn't really well known at the time is that when the Chinese destroyed Fengyun 1C, Canada's RadarSat satellite started doing these swan dives under that debris cloud within 45 minutes of that event. So you can see how fast things change on orbit when somebody destroys a satellite in space. And this is a prime example of what you don't want to see happening on orbit, because if something is destroyed on orbit, the objects basically, they're basically accelerated into high and low Earth orbits simultaneously, and they pose long-term collision risks for other satellites. Now, in order to mitigate this risk, we actually formed an alliance with the Five Eyes and other nations, mostly Western nations, to basically form a deterrence posture to prevent either Russia or China from adopting a more aggressive stance in space. The more allied partners that you have, it actually changes that deterrence posture calculus of belligerence. In order to continue to support that, tracking of space objects is keenly important because it's actually a very, very large volume of space that we have to monitor, and Canada contributes to tracking objects operationally through some of the assets that we've acquired. So the volume of space that we monitor is not light years away. Usually we look at objects that are well within 50,000 kilometers of Earth, and this is roughly the distribution of about 15,000 catalog objects that I took off one of our mission systems the other day. You can see in low Earth orbit, there's lots of congestion, and we're expecting that to become even more congested as we move into the future. Radars tend to cover a lot of those objects there, and they do a very good job keeping track of what's in space. Canada primarily tracks using its space-based Sapphire and Neosat sensors. We keep an eye out in that ring that's further out in geosynchronous orbit. We monitor geosynchronous or deep space objects in particular. They're actually small aperture telescopes are actually well matched for doing that job. And when you take an image, you can take an image with a small aperture system. You can detect these objects. They usually sit around magnitude 12 characteristically if you're observing them on the night side. And we produce thousands of measurements every day tracking on the anti-solar side of the Earth. Looking forward into the future a little bit, the Canadian Forces is developing the Surveillance of Space 2 project, which is going to be a follow-on to the Sapphire operational capability. Its job is more or less to do the same thing, track geosynchronous orbit, but its performance requirements are a little bit more stringent. They want to push down to magnitude 18 or so to look for those basketball-sized objects that we know are out there, but the satellite catalog is so incomplete that we can't actually track them. So we know they're out there because we've seen spot evidence of them existing through very, very large aperture telescopes, but it's actually hard to maintain and track them. From the R&D world, we're working on the next future SSA microsatellite, a follow-on to NeoSat. It's still being settled right now as to what the final form is going to be, but it will have both a geosynchronous mission similar to Surveillance of Space 2, and it will also have a LEO mission where we start tracking objects much closer to Earth in that red blob that you see surrounding the Earth, because we're able to start, we need to be able to get an understanding of how new providers are starting to put systems in low Earth orbit. We know a lot of small satellites are going to orbit in the coming decade. We need to be able to track and maintain custody on them space objects. I have an example that really struck home to national defense back in 2013. We launched the Sapphire satellite with a small space telescope to actually track space objects. And it wasn't even 6 months after we launched Sapphire into orbit, we came within 44 meters of running into a piece of debris from the Defense Meteorological Satellite Program that just came off of one of the US satellites. If they had collided, the closing velocity would have been about 15 kilometers per second, and it would have, well, vaporized Sapphire, or at least make a very, very, very large hole in it on our $80 million investment. So when this happened, it actually escalated the visibility of the orbital debris problem in both low Earth orbit and in geosynchronous orbit to a lot of membership in the Canadian forces. And it really started hitting home that that environment's no longer a passive, safe environment for sure anymore. Things are starting to change quite rapidly. Fortunately, we did not get hit. No, sorry, go ahead.
Are the, in this visualization, are the like the Zeppelin-shaped bubbles, is that like error like confidence intervals or something?
That's right. The name of the game in this world is to take those covariance ellipsoids and shrink them down. The smaller the covariance bubble, the better off you are, because you basically use those bubbles to calculate the probability of collision through a little technique called Foster's method. And if the probability of collision is over 10 to the minus 4, you maneuver your satellite or do something about it. If it's less than that, usually ignore it. So the whole name of this game is to shrink those bubbles down. Now, this is just one problem of space situational awareness. The conjunction problem is rampant. It's something that's dealt with on a daily basis now. But we also use a lot of our sensors to characterize objects in orbit as well. Okay. So if I was to really drill in on satellite conjunction events, a conjunction doesn't mean necessarily that satellites collided. All it means is that they got close enough that the US Strategic Command, who maintains the US space surveillance catalog, basically predicted an event where objects are going to get close to one another. In low Earth orbit for Canada, most of those events happen over Earth poles, and that makes a lot of sense. Most of the satellites that we launch are in 98-degree dawn dusk or polar sun-synchronous orbits, and the natural convergence of those orbits is over the poles. So we see most of those events occurring there. In geosynchronous orbits, it's naturally matched to the placement of geosynchronous satellites in Earth orbit. And if you zoom in on any one of those dots out in geo, there's lots of little individual events where satellites get close to one another. When I made this analysis up several years ago, I noticed that it's actually not pieces of junk that the majority of those geosynchronous objects are basically being represented, or that are the secondaries in those conjunction events. They're actually other Canadian satellites flying in the same orbital slot, but we get close enough from the perspective of the computer that's measuring this and seeing this on the ground that it thinks it actually poses a collision threat. Fortunately, they come close, but they never hit each other. At least we're not aware of it actually happening in geosynchronous orbit. But most of them are actually Canadian on Canadian warnings that we receive. Most of the time we can safely ignore those, but in low Earth orbit we can't. Usually those are debris objects on something more valuable and valuable to Canada. So the SSA R&D project that I run right now is focusing on 4 main areas right now. We do space-based R&D using our space-based sensors. We do space object characterization using the small aperture optical telescopes that we operate. And we also have access to radar capabilities here within Canada also. We're working on a common operating picture. One of the images I showed you earlier actually came out of the prototype that we're working on to basically maintain, monitor, and understand the behavior of objects in space. And I won't show a lot in this briefing today, but that's where that image came from. And we're also working on shortwave infrared daylight sensing capabilities. In the lower right of the screen, the telescope that you see there is actually optimized to work in the SWIR, and we use this telescope during the day to track satellites on the day side of the Earth. So we're trying to get out of the mentality that a telescope only works at night to track space objects. You don't have to. You can work in the infrared band. The satellites are 10 times more reflective in that band. Even though they're harder, the noise environment's actually proportionally larger as well. We can work in that band, and there's a little bit of experimentation that we're starting to do now in that area. One thing I need to emphasize that we work in collaboration with the allied defense labs in the United States, United Kingdom, Australia, New Zealand. The big portion of the work that we do is studying objects that orbit the Earth. Having sensors distributed around the Earth is very critical to do that. Having Canada sensors in space is great for doing this job, but additional capability spread around the Earth really helps us really nail down orbits and get a better picture of what's happening out there. Objects in geosynchronous orbit over Asia are not visible from North America, so I rely on my New Zealand and Australian colleagues to track objects for me when I'm looking for a piece of data on particular satellites. So, and that kind of affiliation is absolutely needed for doing this job. So the space-based and so some of the sensors that we use in Canada for space situational awareness, Sapphire on the far left is the operational capability within national defense. It is a small space telescope. Its design, it is Canada's first military satellite. It's operated by McDonnell Detweiler out of Abbotsford, BC. The sensor can see down to magnitude 16, or objects roughly the size of a couple of meters across, about 40,000 kilometers away. The tracking accuracy is much better than 3 arc seconds now. We're actually pushing better than 1.5 arc seconds, and the astrometric accuracy is very impressive for an orbiting platform that's in Earth orbit. That is the key contribution that we make to the space surveillance network, is through that operational capability with Sapphire. And it runs continuously, producing about 3,000 object measurements per day on geosynchronous objects, and it is running continuously right now. And we get a little bit of data access if we were wanting to see something. The sensor I run most often at DRDC Ottawa is NeoSat. It's a dual mission microsatellite that we developed with the Canadian Space Agency, and it was designed very similar to Sapphire, but we don't have the same level of redundancy and resiliency built into the vehicle, but we're actually been able to pull off some pretty incredible space surveillance, space situational awareness measurements in recent years, and I'll talk a little bit more about that in a minute. The ground-based optical telescopes, we have 3 robotic ground-based telescopes in Canada located at our labs at DRDC. We use them primarily for tracking geosynchronous objects, but we do some tracks of LEO objects from time to time if something's interesting. I remind everyone that I don't usually track objects in space just out of the goodness of my heart. If you're getting a phone call from me, that means your satellite is wounded, hurt, or something worse. And I'm kind of the grim reaper of satellites when it comes to tracking of space objects. A satellite that's working normally is not really that interesting to me, but if something's happening, that's when it becomes interesting.
I have a question now about the previous slide. Is there anything particular about NeoSat that's different from Sapphire, and why it's being used for exoplanet characterization? I mean, they look very similar in terms of sensitivity and pointing accuracy.
That's a good question, a good point. Mechanically and instrumentation wise, they're very similar. Sapphire was built for one job, which was space surveillance tracking. NeoSat is a space telescope, pretty much pure and simple. There's a lot more control and authority that we have over the vehicle as to how we orient, point, and how we shoot with the vehicle. We got a lot more flexibility built into it. One of the key mechanical differences is that we don't have a lot of redundancy on board. Microsatellites are not the same thing as small sats. To the layperson, that may not mean a lot, but in the actual mechanical and the electrical design of the vehicle, we're single string, which means that if one power circuit dies, the entire vehicle dies. If we only have we don't have a backup computer on board, in order to benefit from the low-cost nature of microsatellite technology design, you have to pick your parts very carefully and use very small teams, but you don't have a lot of redundancy built in. The cost of Neosat was about 1/5 of that of Sapphire. There was a lot more redundancy and capability and performance reliability built in. Neosat, we don't have that same requirement as the military does. On Neosat, we have a lot more flexibility to repurpose and change. Neosat is also an R&D vehicle. For the military community, an operational configuration is locked down hard, which means that you do not change the software, you don't change the data processing pipeline at all unless it's a very managed process. On Neosat, we have that flexibility. We can repurpose, we can change the flight code if we need. We can make those alterations because the end customer in the space surveillance network doesn't really expect us to be providing a very consistent data throughput. If something interesting happens and we need to repurpose the vehicle, we have that flexibility on board Neosat. We don't on Sapphire.
Okay.
Okay. So talk a little bit about the ground-based tracking. So when we track geosynchronous objects, the image that you see on the right, you should see a bunch of stars trailing in the background. You'll see those dots in the foreground. Those are geosynchronous objects that we tracked in 2017. There's a Canadian satellite, Nimiq 6, in the lower right, but you may notice there's another satellite dot at the very top called AMC9, and it's actually drifting slowly relative to the others. AMC9 was a satellite that fell out of control in summer of 2017 and started spinning on orbit. And if you look closely, you'll see that it actually flashes, and by taking measurements of the photometry on AMC9, I produce a phase curve that you see here, and I can look at that that rotational phase curve and basically say, yeah, that satellite is uncontrolled, because a healthy geosynchronous satellite does not do this. It does not produce an oscillatory light curve from the dark or the front illuminated portions of the solar arrays on the satellite. Basically, it produces nice, smooth, monotonically increasing light curve on the vehicle. And this is one of the techniques that we use to instantly assess whether or not if an object's stable. AMC9 did loops around several Canadian satellites during its little gallivant around geosynchronous orbit back in 2017. The operator did regain control and actually successfully decommissioned the vehicle. But this is an example of what does happen on orbit. Periodically, these things do lose control, and we have to track these things. So we're going to change gears a little bit here and talk about some of the LEO tracks that we've done. We work with some universities on testing technologies for safe spaceflight operations. And the CanX 7 satellite, but from the University of Toronto, we contracted them some time ago to develop a drag sail technology to deorbit nanosatellites from orbit much more efficiently. Everybody knows that small sats is a booming industry right now. What tends to be forgotten about is that those satellites are so small and compact. They have very, very high ballistic coefficients, and as a result, they tend to be long-lived in high Earth orbit. The intent of the drag sail was to basically remove the satellite from orbit much more efficiently, and to see if we can get it to re-enter within a few years rather than the 75 years that would have taken it naturally to deorbit. So the long story short, the test was successful. Right now, CanX 7 deployed its drag sail, and we were able to confirm that, well, sort of validated optically that the sail was deployed. And right now, we expect the re-entry of the vehicle in probably sometime in the next 3 to 5 years. The next slide, I'll have a bit of a track that we took on CanX 7 during the sail deployment. Now, we don't get to see the sails unfurl, of course. All we get to see is basically the brightness shift when the first drag sail is deployed. And I'll play the video now.
I am arming the -Z sail.
CanX 7's in the upper left video, upper left box, and we have the slight curve also.
Sails armed. Sending the fire command in 3, 2, 1, fire.
Whoa.
Go ahead, throw it up.
Magnitude increase of 2, just brightened by 2 magnitudes. 5 times the area. RMC, can you confirm brightness increase?
Go, definitely, yes.
Excellent. We confirm optical change on CAMX7. Looks like your first sail deploy, guys. Congratulations.
Thanks. Our telemetry looks good as well.
I'm not sure if the audio came through on that video or not, but we were able to work directly with the operators during the drag sail deployment. One of the reasons we did that was that an in-situ camera on board the vehicle failed, and we wanted to have some validation that the telemetry from the vehicle actually reflected a change optically. And if we did see the object flare up in brightness, we could basically say, yeah, your sail deployed. So that cross-sectional change that would occur on orbit basically gave us a very good indicator that the first sail deployed. The 3 other sails deployed on the subsequent orbits, and the CANX-7 actually became naked eye visible for a short period of time during the tracks. So we're pretty happy to see the results and actually to do some validation. This is one of the first times we've actually worked with a satellite operator real time to watch what they were doing in orbit to infer and measure and understand what's happening out there. The satellite was only 700 kilometers above the Earth, and we were tracking it with one of our cameras to basically ensure that things were taking place. And for us, it was a real bonanza because we don't usually see satellites drastically changing shapes like this. For us, it was pretty interesting. So now I'll move on to the NEOSAT. NEOSAT is a dual mission microsatellite for astronomy research, space situational awareness, and development, test, and evaluation. It's a joint project between the Canadian Space Agency and DND. There was 2 reasons we got the money to build NEOSAT. The first one was to do a military utility assessment of the microsatellite platform. Back in the early 2000s, nobody trusted small satellites to be doing jobs that were useful for military or even governments at the time. They were not trusted at all. So we're one of the early investors into trying these technologies out to see whether or not they could actually play a role for the military here. We also did the other reason was to do experiments from space that cannot be performed from the ground. And for doing space situational awareness experiments, there's no better place to do it than in space, of course. So primarily when we track objects from NEOSAT, we track pretty much those blue dots anywhere outside of that red exclusion region. The exclusion region, of course, points towards the sun. Our orbit is at roughly 800 kilometers in a roughly dawn-dusk sun-synchronous orbit. We pretty much track those objects in geo pretty much anywhere we want and how we want. It depends on the experiment that we're running in any given day. The continuous viewing zone, similar to the most microsatellites, about 54 degrees across. We can track pretty much any object in that region more or less continuously for up to about almost 2.5 hours. And basically, if the satellite goes into that region, we can pretty much pick them off continuously because we have lots of background stars for the star tracker on NEOSAT to get a lock, point at the vehicle, and start acquiring imagery. So some key findings on the military utility. We're good to about 2.4 arc seconds of accuracy. We've actually improved that since I've drafted the slide. We see objects down to magnitude 16, but we've actually improved that quite a bit in the last year after working with Jason Rowe, and we're actually able to push down quite a bit further now, which is very impressive. We had a prolonged commissioning period on the vehicle. It wasn't great, but after we got through that commissioning, the agility of the vehicle was exceptional for doing a lot of R&D, especially when you're trying to track objects close to you near the spacecraft itself. And I'm talking about objects anywhere between a few thousand to even down to about 8 kilometers. So I'm doing photometry on objects that are basically within kilometers away from the vehicle on some occasions. Some of the accomplishments, we worked with our UK friends to track a military satellite relocating in geosynchronous orbit. One of the things that surprised me was that when a big geosatellite moves in orbit and relocates to another position in that belt out in geo, we actually lose track of it for a few days, which is surprising for a big 6-ton vehicle to be kind of cruising around out in geo and nobody really knows where it is. But using space-based and ground-based sensors, we're able to reacquire and keep good custody of these objects when they do so. We had some good tracks on the AMC-9. We found one of the debris fragments that came off of that vehicle during its uncontrolled flight around Canadian satellites. And in 2018, things changed quite drastically for us. We started doing co-orbital tracking of objects, which was a pretty big change for us. And even cooler, we're actually able to watch space objects and space debris conjuncting with NEOSat itself, which is pretty neat because we didn't expect how easy that was going to be. So I'm going to show you an example of this. This is the Spot 2 satellite that we tracked from NEOSat, and on the upper right you can see basically the photometry that the imagery that we get off of NEOSat. You notice that the stars in the background aren't shifting. One of the neat things about observing a conjunction is that they're coming at you at a constant bearing decreasing range scenario, which is very similar to a collision scenario in a Navy. In space, that means your stars are fixed, and all you got to do is point your telescope in the oncoming direction of the object that's about to hit you, and you'll get all kinds of tracks. Now, when we set this imagery up, we overexposed the imager. We didn't know how close and how far and how bright Spot 2 was going to be, so you'll see a lot of blooming on the image here. So we're getting a lot better at this now. But you can see how efficiently we can track space objects, and this is allowing us to test a few ideas about whether or not we could allow satellites to autonomously decide if they have to maneuver out of the way or not. Because one of the cool things is that the objects, before they conjunct with you, are visible on half-orbit intervals prior to the time of closest approach. So you have several opportunities to measure the object that's coming toward you in order to actually decide whether or not you got to do something about it. So there's possibilities here as to whether or not we could actually do autonomous collision avoidance. In June 2018, Sapphire was observed in very close range to NEOSat. NEOSat and Sapphire were actually launched into orbit on the same rocket, PSLV C-29, if I remember correctly. And one of the neat things about that is that each satellite has its own orbital period, but every 14 months or so, they get close to one another. And the last time that happened, about a year ago, we were able to take this track set on Sapphire, and again, we overexposed the imagery. We didn't know how to set the imager when we were making these acquisitions, but we were able to actually acquire some co-orbital tracking on the vehicle down to as close as 8 kilometers, and you can see basically ghosts and shadows being scattered within the optical tube of NEOSat as a result. So you know that your target object's very close when you start to see shadows like that being cast in your optics. So it's a pretty neat way of trying to keep very good custody and protect a Canadian Forces satellite periodically. You might notice a few snowstorms in the background there. That's the South Atlantic anomaly. It's a radiation region in Earth orbit that we tend to hit every once in a while, but it's just a cost of doing business in space. And finally, as a demonstration for some others, just actually a couple weeks ago, we took this image of the RCM satellites after a few days after launch. NEOSat was over northern Ontario while RCM was flying over Florida at the time, and we had just enough orbital data to try to get a track on RCM. The funny glow you see in the background is basically dayside Earth glow scattered down the optical tube of NEOSat. We don't usually point this close to the Earth limb at that range when we're trying to watch objects, and that's why we're starting to see these funky backgrounds on the imagery when we collect them. The fortunate thing was that we took the photometry on all the satellites. They were all pretty much all within 0.1 magnitudes of each other, so we knew we were looking at 3 objects, roughly the same attitude, orientation, and size, which was really good to see. And this was the first baby picture of RCM on orbit just after its launch. And actually, I've seen some very good videos from the Cassiope mission, actually, where they got some short video tracklets on that trio as they were flying in orbit as well. So some experimentation that's coming up. We've worked primarily with optical telescopes in recent years, but we're starting to look into using the very large Algonquin radio telescope to do some radar tracking of GEO. in particular to see what kind of space object identification capabilities that sensor may have. It was recently converted to a space surveillance sensor, and it can actually position and target satellites in geo orbit down to within about 10 to 20 meters. For our work, that's phenomenal. And we're going to be working with the data provider, Hoth Technologies, very shortly to be doing some particular experiments with that telescope shortly. The situation in orbit, like I said earlier, is changing. On-orbit servicing is taking place. Satellites are growing arms, and they're actually starting to reach out and grab other satellites. And there's actually an event taking place this December where we're tracking space objects in GEO that are actually going to be servicing another satellite. So that's something that we're looking forward to this year. Future space surveillance architectures, we're going to be helping to work on the Surveillance of Space 2 platform, and also the current initiative for the next SSA research and development microsatellite is ongoing right now. There is another SSA microsatellite in development right now. The context of the SSA capabilities have been set, and now we're going to be putting it to industry here very shortly to come up with a proposal for exploiting that new capability on orbit. And we're hoping to see some high performance capabilities come to bear. There's a lot of things that I love about NeoSat. There's a lot of things I really, really, really wish it had. EMCCD that frames really quickly, I wish it had. I wish it had the ability to change its gain state. If it could maneuver out of the way. There's a lot of things I'd love to see on the vehicle, and I'm very keen to see how Canadian industry responds to that. We're also running an innovation program looking at space situational awareness. We have 10 contracts that are currently ongoing or completing currently right now. And there will be a call actually that is coming out soon in the area of space debris mitigation and tracking, and another one in satellite defense. So there's a lot of exciting new things that are taking place here, and we're keen to see how things play out. So I didn't really get a lot into exoplanet work. If I really encourage for anyone who wants to talk about that kind of thing. I know this is an exoplanet community full of astronomers. The work that we do on NeoSat is kind of like the other mission next door on board the vehicle. We support a lot of that work with Jason Rowe. The Canadian Space Agency is opening up an announcement of opportunity for access to the vehicle for accessing data on the vehicle. The amount of flexibility on board is pretty good. We've got some limitations just simply because it is a microsatellite. It doesn't have all the bells and whistles that we really wish it had, but it's one of the capabilities that's on orbit right now, and we're able to sustain and keep the thing going so long as there's interest in the capacity of the vehicle. So if any of the data that we take for astronomy tasking is pushed out into the Canadian Space Agency's open data portal, and those images are identically spot on to the same ones that I see for the space surveillance taskings, with the caveat that we don't put the space surveillance taskings out on the internet. We do have a defense and security experimentation role assigned to them, therefore we don't share those publicly. So anyways, I know there was a bit of a fire hose of SSA research and development, and I'd be happy to take any questions you might have on some of the work that we've been doing. Thank you very much.
All right, thank you so much. Yeah, I open the floor for a couple of quick questions.
Hey, that was a very interesting talk. Thank you. So you made a reference to the Navy and like ship collisions, and that got me thinking about sailing regattas back in the day. And I was wondering whether if you can have satellites kind of detect each other, are there already conventions established for which one should change course the way there is in a sailing race? It's very clear who has to deviate to avoid a collision. Is there such a thing in the three-dimensional environment in space?
I'm very glad you asked that question, because the answer is no. In practice, most of the secondary objects that are going to collide with an active satellite that you really care about, most of those secondary objects are debris objects. They can't maneuver anyway. So if you have the ability to maneuver and you're confident enough in the data that you should maneuver and it's warranted and it's not going to affect your mission that much, usually they will maneuver. If you look at RadarSat-2 operations or even RCM, they will be doing this fairly frequently, once a month or maybe twice a month in some cases. depending, or I know RadarSat-2 does about 2 maneuvers a year to maneuver out of the way of some space objects. In slightly higher altitudes, the debris environment is actually that much more that operators have to maneuver quite a bit more frequently. So there are no real defined rules of the road. There are a set of recommendations that the United Nations is starting to push forward right now toward trying to create norms of operations in space. And it's actually a very promising thing because all the countries signed on to it just last week, which is really promising. So there's starting to make very promising moves towards creating a degree of normalcy as to who does what in orbit. But to simply answer the question in the practical sense, usually it's a debris object. You got to maneuver yourself if you've got that ability, because the debris object is passive. There's nothing you can do. It can't do anything about it.
Lucky, this is Frederick at ABB.
Hi, Fred.
You mentioned that the satellites are brighter in the infrared. Can you comment on the rationale? Is this because of the MLI that they're covered with, or?
There's been some work that's been done on spectral BRDFs in the 2 to 4 micron band, and what we find is that they tend to be very strongly reflective in that wave band, which is very fortunate because in that band the daytime sky is very dark. It allows us to actually see these things. So there is a lot of literature in the study of the BRDFs in that wavelength. Of course, AMOS is a very good reference for quite a bit of that, and I know Donald Bedard has done a little bit of work in that area, but mostly he's worked off of a lot of the work done by NASA by examining a lot of the spectral BRDF work done by that community. So I said in the number 10, it was just basically an order of magnitude. It was basically just a very fortunate window in our optical spectrum that we could see these objects. One of the thing I should remind everybody is that we're finding there is a new technology that's appearing right now, which doesn't use SWIR. It uses visible light. Event-based cameras have this strange property right now of seeing satellites during the day. And I'm not sure if anybody's familiar with that technology in this community or not, but they're pixels that basically trigger as soon as a small change in brightness occurs. And oddly enough, apparently these things are able to detect satellites in a clear daytime sky. For us, that's very compelling because that drastically reduces the cost of doing measurements of objects in LEO. If it pans out, we don't know the sensitivity and we don't know the performance of them, but if they could be made to operate in the shortwave infrared, there's a very big bonus that could occur if that kind of technology could be exploited, because you put a lot of radars out of business if we can put small optical sensors in nice desert areas to track and maintain positions on or track objects in the catalog.
And maybe just a small other question. In all the data that you've looked at from NeoSat, did you ever encounter like a streak from an object that you couldn't relate to any object that's currently part of the catalog, the known objects?
Oh, it happens all the time. There's the public catalog that's available from U.S. Strategic Command is actually only a subset of a much larger catalog that they maintain. The ones that we see in the public catalog are the objects that we've been able to put our hand on our heart and say, we know the country of origin where they came from. There's about 8,000 objects that we are tracking in orbit. We don't know who the origin is. They are known objects, but we simply just don't know the origin country, so we can't declare fault or in some cases declare attribution towards the owner nation in those cases. So it does happen quite often. There are a lot of objects in geosynchronous orbit that are simply defense and security missions. Their orbital elements are not published in the public catalog. Those objects are detectable by other nations. They are visible, but the orbital ephemerides for them are not produced. And sometimes we do encounter those objects. We conveniently set that data aside. So largely because of the alliance relationship that we have with our U.S. friends at Strategic Command. So yeah, it does happen. There's quite a few objects out there. The Mysterious objects, mystery objects, we do see them. Things do streak through the field all the time. Usually we don't have enough data to do anything meaningful with it. But there is a catalog of other data that does exist where we simply haven't attributed the owner nation. And they can be in the ballpark of anywhere between 6,000 to 8,000 objects. Strangely enough, too, there's other cases where we've lost objects for years at a time, and the objects are actually known, are actually the owner nation's known, but simply because we haven't had enough sensors, the objects were lost in orbit. After 30 days, I think that's the rule. If the object's lost for 30 days, we usually can't find it again. And then there's a very large and manpower intensive job to reacquire and figure out what object that was. So you do see objects streaking through the field all the time. The big challenge in space-based observations, though, is to differentiate, did my detector get hit by a proton, or is this a legitimate satellite streak that I'm seeing? That's more often the case that we're dealing with NEOSAT on a day-to-day basis.
Hey, Lockie, Brett Gladman here in Vancouver.
Hi, Brett.
So on the subject of sensitivities, you had mentioned doing considerably better than 16 with Jason. Can the satellite do a sidereally attract 1 minute exposure, and what do you think you can get to?
Oh, I have to talk to, we're working with Dave Ballum, actually, out at University of Victoria. And he's claimed that he's been able to punch down to asteroids down around magnitude 20 now. Now, they've developed quite a bit of background noise reduction techniques in the last year, and we've been able to push down to around that level, but we do stack the imagery when we do that. For a single frame image, I have seen objects, well, let's see, the faintest asteroid that I've tracked was a 10-meter object that came in from the moon, or just inside of lunar orbit, and that was pushing magnitude 17 when it came in the side of lunar orbit. But I think it's around magnitude 19.1 typically, but we can stack down to magnitude 20 if the approach is correct. I think we're working with 3 to 6 frames when we stack them for about 1 minute exposures. I don't usually expose the imager that long. 60-second tracks is death for satellite space surveillance, but it's in the ballpark of around magnitude 20 now when you stack the imagery.
Okay.
Yeah, I have one more question. I mean, you presented that that you're doing obviously an effort from the ground and an effort from space with things like NEOSAT. What are the relative contributions from this? What are the kind of advantages? What are the efficiencies? Because I would think that these things in space have a much higher price tag than putting a few 35 centimeter telescopes on the ground.
Yeah, that's a very good point. One of the limitations that I have to deal with as a part of the government of Canada is that if we place a Canadian government asset in another nation, I have to create an agreement with that other nation. So I got to start working with the embassies and so forth to allow the placement of that sensor on that country. Because ideally, I'd be looking for a nice desert place to be putting my equipment to do the job. That takes time, sometimes in the order of 2 to 3 years, just to get the agreement in place, and that's even before you start building and constructing a facility. So there's basically a diplomatic and basically an agreement, political matter that has to be addressed first of all. Here in Canada, these ground-based sensors, well, here in Ottawa, I can usually say the sky's clear about roughly 30% of the time here in Ottawa that I could do the job. It's a little better out in our sensor in Suffield. Valcartier, Quebec is, well, I don't think I've ever seen a clear day in Quebec in probably the last 10 years we've been running the sensors there, but it does happen. The sensors out west, we usually push around 40% clear sky availability. The sensors on the ground, to buy the equipment, it's about $250,000 to get the right equipment to have a nice, reliable, remotely controlled facility for doing this job. The real downside is weather. That's the piece of the puzzle that really works against us. And Canada is a country that's fairly far north. We don't get to see as much of the geosynchronous belt as we'd like to. We have to look very low elevation through a lot of moppy atmosphere in order to actually try to see geosynchronous orbits. So we have very high, we've got a lot of extinction at low elevation angles when we try to observe geo objects from Canada. So there's a few things that work against us on the ground. The thing I do like about the ground-based opticals, though, is that they're very good for doing all-night photometry on geo objects. So there are some very good pluses to the ground-based facilities, and that's why we do maintain them. Space-based, you are correct. There's usually a 4-year build time to build any satellite. They are expensive to build. The maintenance is not negligible for a satellite system. Here in Canada, the ground link is actually a surprisingly expensive thing to do for a small satellite in Canada. So it costs me roughly about $300 to $400 per pass, even if I only transmit a few bits of data. So it's actually a pretty expensive thing to operate. There are cheaper ways of doing the job, but that's a rough number that I tend to kick around just so when I'm planning the operations for any given year. In space, you don't have to worry about the atmosphere basically extincting any of the images for you. So it works really well when you're trying to see stuff further out into space. You don't have to worry about urban light sources. The day-night weather cycle, you can forget about it. I can track right towards, I can go to about 45 degrees off of the sun, tracking some objects in geosynchronous orbit. If there's something that I want to persist on, I can do that. There's a lot of pluses to going to space simply because of the optical environment's pristine. One thing that we do have to work against is the proton environment in space. It can be atrocious. We're always hit by charged particles of some origin or another, and that produces little streaklets on our image, and a lot of times they look like dots as well, so it's very hard to tell what is a satellite and what is a proton hit on my camera whenever I'm tracking imagery. We use a lot of stacking to get around that problem. It's a very effective way of getting rid of proton hits, which are random in nature. But it's one of the downsides. But it's been a fantastic way to make a contribution to tracking in orbit. And plus, you can start doing things in much closer proximity to satellites as well if you pick your orbits right. And that's one of the things that when we've launched with Sapphire, just by virtue of being on the same ride, we're able to do science that we never envisioned originally. So we're able to do some things that were pretty unique, and that's one of the other advantages of going to space.
All right, so if there are no more questions, I think we are a bit past the hour anyway.
Yes.
Then I would like to thank the two speakers again. Thank you for these two great talks. I think we really want to kind of encourage this collaboration also between our what is maybe mostly exoplanet community and in industry and our partners in Canada. So it was very great to have kind of an outside talk on a slightly different subject. Thank you so much.
Thank you very much. Have a good day, everybody.